Thank you very much, guys, for being here. We're going to talk today about CO2 transcritical systems, basically how the system is designed from the start, why we need CO2, and how the system operates. There are different technologies as well that we use. We will discuss some of those, and we'll talk about what is normally used in the field right now. So we're going to talk about CO2, what is CO2 as a refrigerant, some of the safety features that we need to consider, the design concepts that we have, also what are the main subsystems and components, and what is available on the controls portion from the different controls manufacturers. So why are we talking about CO2 today, or you see, or you hear a lot about CO2? Well, CO2 is not a new refrigerant. It has been used for a long time. In the early days of refrigeration, actually, ammonia and CO2 were the main refrigerants being used. And when I say early days, that's 1800 something, 1840, 1850. So ammonia and CO2 were the main refrigerants. And those are great refrigerants. What happens, at least with ammonia, ammonia is toxic and mildly flammable. That is the main reason why ammonia is not being used in supermarkets. However, ammonia is highly used in industrial applications when they have bigger loads because ammonia is the best refrigerant that we can have. It has a lot of cooling capacity, and it can remove huge heat loads from the space with a small amount of ammonia. CO2 as a refrigerant is good as well. The problem with CO2 in the early days is that it's a high-pressure refrigerant. When I say high-pressure refrigerants, it's about more than 10 times that you will see with HFC systems. So that was the downside at that point. Because of that reason, the chemical companies, they created the synthetic refrigerants, and some of those, they call the family the CFCs or HCFCs. Those are synthetic refrigerants that they do the work. They produce cooling in the store. They cool the product that we need. But when those refrigerants are released to the atmosphere, they were causing some issues. The problem with those refrigerants here, this family, is that they were damaging the ozone layer. So because of that problem, there was some regulations that they were banning those refrigerants. And that happened, well, still we have R22 in some installations, but that is going away. So with that ban, the chemical companies continue making changes on refrigerants, basically chemical compositions, what they are made of, and eliminate the chlorine portion and come with this new family, the HFC refrigerants. That is what we have right now. That's what we are still using. The 404A, 448, 449, 407F, all those refrigerants, they fall into the family of the HFC. Now, those refrigerants, they do not damage the ozone layer. The problem with those now is that when they get released to the atmosphere as well and they break down, they do not break down completely, and part of that keeps the heat in the earth instead of releasing the heat to the space. So that is causing what we know now as a global warming. So those refrigerants, they do have a number assigned to them that is the GWP number, this GWP. That number is relative to CO2. Basically, the higher the number, the more effect they have on the global warming potential. So CO2 is referred as GWP of 1. Some of those refrigerants, they have GWP numbers in the thousands, like almost 4,000. That means they cause, let's say, 4,000 more damage than CO2 when they get released to the atmosphere. Because of that, the new family of the refrigerants here is the HFO family. Those refrigerants are still chemical refrigerants. They have different composition. They do have a very low GWP compared to the existing HFCs, but now they have something that is called the PFAS substances. The problem with those is, again, when they get released to the atmosphere, they break down. After some time, they will fall into the earth again, and those substances can contaminate the water streams in the earth. So that is still a problem if we release some of those refrigerants here. But even though we have those HFO refrigerants, we still have the natural refrigerants. And CO2 and ammonia and propane now, they are refrigerants that we can handle better than we had before. And those are, again, natural refrigerants that they do not damage as much as the chemicals. And also, they are efficient refrigerants that we can use to produce refrigeration for the supermarkets. CO2 as a refrigerant can operate in different modes, let's say different modes. One of those is subcritical, and you have heard now about the term transcritical. The difference between CO2 subcritical or transcritical is that part of the system, when the system operates all below this line, which is a pressure about 1,070 psi, when the CO2 system operates below that pressure point, that will be a subcritical system because this highest point here is called the critical point. So anything above that will be transcritical, anything below that will be subcritical. So if we have a system working like this, it will be subcritical system. Probably you have heard about the term cascade systems. If you have a cascade system with CO2, your CO2 portion will be in subcritical mode. Now, if you have a system that operates, or part of the system operates above the critical point, that will be a transcritical system. In this case, that's the system that we will be discussing, transcritical system. We are not gonna, well, we're gonna talk about a little bit about cascade systems, but mainly will be transcritical systems here. Some of the properties about CO2, some important properties, is that we cannot see it, we cannot smell it. Also, CO2 as a substance is heavier than air. So what happens in that case is if there is a leak of CO2, the CO2 will fall to the ground and that will displace the air to the top. So that is important to know when we install the leak detection systems, and we will see why. CO2 as a refrigerant is also cheap. It's not expensive right now. But here we have a table where we compare different refrigerants, HFC mostly, against CO2. If you notice here, one of the things that is similar between HFCs and CO2 is that all of those are classified as A1 refrigerants. All of these are A1 refrigerant. Now, what does A1 means? Well, A1, based on the classification from ASRI that you can see on the table on the right side, means that is non-toxic and non-flammable. At least non-toxic in low concentrations. And that applies for every refrigerant. All of those are toxic in high concentrations, but they are non-toxic in low concentrations. That's what the A1 means. And CO2 falls into this category, A1s. We have propane and ammonia. We discussed those two. Ammonia is highly toxic and mildly flammable. And propane, we know for sure, is highly flammable. It's an A3 refrigerant over here. So we can use all of those three refrigerants in different ways. Like ammonia can be used if the system is outside of the store. That will be one thing. For propane, we can use propane, but we can use only a small amount of propane in a refrigeration system. We know the limit right now is 150 grams. They are trying to increase that, but as of now, it's only 150 grams because of that reason, because it's highly flammable and explosive. So again, here, the important part is that CO2 is A1, and we can use it with the amount of charge that we need. There is no restrictions on how much CO2 you can put in a system to operate that. The difference of those will be this part about the GWP numbers. We mentioned the GWP is basically how much impact they have regarding the global warming in the Earth against or compared to CO2. CO2 has GWP of 1. All of those refrigerants, they have more than 1,000 GWP number. The new A2Ls or HFOs, they are about the 150 number, and they fall into the new classification that complies. But again, they are related to the PFAS, so they may not be commercially available right now, or maybe some restrictions on how we can use those refrigerants. The other part here is about CO2 as transcritical system. We mentioned CO2 transcritical and subcritical. Well, HFC refrigerants, they also can have that mode way of operation. However, all the HFC refrigerants, they operate in subcritical mode because their critical point is too high, it's like 150 degrees or something. So all of HFCs will operate in subcritical mode. If you hear the term transcritical system or transcritical refrigeration system, the only system that you can talk about that in that case will be CO2. There is no other refrigerant right now that will operate in transcritical mode. It's only CO2. CO2 has been in the market, not only here, but in Europe. Actually, they have many more systems than we do since probably 2000. Europe has about probably 60,000 systems right now. In the US, we have about 2,000, probably 2,200 maybe. So we are behind what they are doing. And part of the reason for that is because they do have regulations, or they did have regulations implemented early that they were pushing for low GWP refrigerants or natural refrigerants. So you see here the F-gas regulation in Europe. Now we see some regulations here in the US, especially in California. In 2022, they have the new rule that if you have a system with more than 50 pounds of refrigerant, you need to install low GWP refrigerants. Well, that rule is expanding, and now the EPA has released something that will apply for us between 2026 and 2027. Starting on January 2026, systems for cold storage will have to use refrigerants with GWP less than 150 or maximum 300 if they have a cascade system.
New systems.
New systems, yes, new systems. The retrofit portion is not still finalized, I think, but this is for new systems. In the case of supermarket or full retails, that will be until January 2027. But at that moment, will be the same thing. For new systems, they have to have GWP less than 150 or cascade system 300 and below.
You know what's the limit right now?
For California, 150.
150 right
150 right now if you have more than 50 grams, more than 50 pounds of refrigerant for new systems. Yeah. Well, that is California. Everywhere else, they don't have a limit for that. You can install steel for 448, 449 in other states, but not for California.
That has changed this
Yeah,
year.
we will see changes. Well, that also for condensing units, they have a limit that will be 2026. There's something else in this West Coast is about the state of Washington. Washington, they do not have strict regulations of what refrigerant you can use, but now they have this new rule that they need to report what refrigerant they have, what leaks they have on the systems, and they have to fix them real quick. If they have between more than 1,500 pounds of refrigerant, they need to be reporting right now how much refrigerant they have, and if they have leaks, they have to repair them. Also depends on how many, well, this one is with systems more than 50 pounds, and that applies for air conditioning and refrigeration, not only refrigeration. So those are new rules that we are seeing that will push faster the use of natural refrigerants or low GWP refrigerants. Talking about safety on CO2 systems, there are different things that we need to consider. First, I want to say that similar safeties that you have with HFC, same apply with CO2. In addition to that, we need to consider a few more. So, one of those is that, again, CO2 is a high-pressure refrigerant, so we need to be aware of what system and what part of the system we are working on. Because the pressures of CO2 system, they can range between 150 pounds up to 1,500 pounds. If we talk about HFC systems now, the pressures range between maybe 2 pounds up to 350, 400 maybe. But CO2, we are talking about 4 to 5 times of that pressure. The other thing about CO2 that we need to be aware of is that CO2 expands really quickly. It has what we call high coefficient of expansion. So if we have CO2 liquid especially trapped in a part of the system that has no way to release or escape, that can increase the pressure really quick if you increase the temperature as well. And that can actually break the pipe in some situations. We have seen that happening. So it's very important to make sure that you do not trap CO2 in the system, in any part of the system. So this is an example of what would happen if we increase the temperature of CO2 in 1 degree when CO2 is at different conditions. So if you have a CO2 at minus 20 degrees, which minus 20 degrees is about the normal low temperature suction, the suction temperature for systems, at minus 20 degrees, your pressure will be about 200 psis. If we increase that only 1 degree going to minus 19, your pressure actually increased 4 psis more. Well, that is a little bit different if you are at 50 degrees. 50 degrees, going from 50 to 51, your pressure increases 9 psis.
Per degree, right?
Per degree, yes. So if you increase 2 degrees, that will be 18 pounds, and move on. So at 69 degrees, your pressure increases 11 pounds. I mean, your pressure increases 11 pounds. So because of this, it's very important, again, not to trap CO2 in the system, because assuming that we have a store and we lose power, the refrigerant in the liquid line is about 36 degrees, but the ambient temperature in the store normally is about 75 degrees. So if the liquid stays there and increases from 36 degrees to 75 degrees, your pressure will go from 520 psis down up to 900 psis if we don't have a ways to have that CO2 released from the store. So what do we do? What options we have for that? Well, there are different options either for service or for operation of the system. If you have a display case or evaporator that you are servicing, normally you want to isolate that part of the system, right? So we do have this option with these valves. We call those valve stations. It's basically a ball valve with a check bypass around. You can have those manufactured like this with the 2 different components, or these valves, they already have the check valve integrated on them. So that simplifies the operation and the manufacture of the systems. Because instead of doing this subassembly, you have only 2 joint brace points that you can do, and then you have your check valve with your ball valve at the same point. Those valves over here, there is a limitation on sizes, basically. Those go from 3/8 up to 1 1/8 sizes. But those valves, they are rated for 1,300 psis. So you can use them easily in many parts of the systems.
You always want the A facing towards the evaporator, right?
Yes, exactly. I was going to go to that, like this. They do not have an arrow direction on the check valve. The way they identify that is with the A. This valve is hard to see here, but the valve has an A letter on one of the ends. So you need to put the A facing the evaporator, and that means that the release of the check valve will go back to the compressor rack.
Now, I've heard that they've had issues pulling vacuums from the rack to the cases because of these valves. Is that true or not?
Normally, no, unless, let's assume that you have the valves, but for some reason you don't have the coil. If you don't have the coil and only close this isolation valve, the check valve is pointing to the compressor rack, so you will still be pulling air, let's say that. But if you have your system closed, you should not have problems pulling the vacuum. Because this valve is a ball valve, so you can open the valve and still pull the vacuum. That should not be the problem.
So the only way they would have an issue if it's piped in backwards then, right?
Pipe them backwards, yes. Well, pipe them backwards and have the ball valve closed. That will be the only way that you can have that issue. Or, again, if you don't have the coil for some reason and waiting for the parts to come, you basically need to seal this end of the valve so that you don't pull any air from that side.
Yes. Yeah. I've been hearing rumors that they're saying because of valves are not able to pull proper vacuums inside the cases from
Shouldn't
the
be the
rack,
case.
and that they've had to go into the rack, into the case to pull a vacuum.
No, it shouldn't be the case. We have that installed in many, many stores and no problems.
Okay.
The other thing is in CO2 systems, you will see a lot of pressure reliefs. That is something that you normally don't see on HFC systems. On HFC, you will see pressure reliefs at the receiver only, and that's all you have. With CO2, again, because of the high pressures that we operate the systems at, we need to have more pressure reliefs just for safety to ensure that nobody gets hurt or anything. So you will see multiple places with pressure relief valves. Those pressure reliefs, they need to comply with the ASRI code, which they require those pressure reliefs to be UV or VR marked. That means they were certified according to the requirements that they need, which is basically the Pressure Vessel Code 15, Section 8. That's what they need to meet requirements for. So the vendors, they will have those valves, and if you get a valve from any of the vendors, just check that they have the UV or the VR mark, and then you will be able to use those. Another important part is that those pressure reliefs, or the pressure reliefs, some of those are rated for vapor or liquid operation, not all of them. Some valves are only rated for vapor. So be sure or check your valves once you're going to install them. If that's a liquid line, your pressure relief has to be rated for both liquid and vapor. If that's a vapor line, you can install basically either one. But if you have a vapor pressure relief installed in a liquid line, it's not going to do the work that it needs to do. So be aware of that part too. The compressors. The compressor manufacturers, they have installed pressure reliefs on each compressor. In the past, they had relief valves on the suction side and the discharge side. For some reason, they have only now, some of the vendors, they have only one valve on the discharge side, not on the suction side. But still, the point here is that those pressure reliefs that you can see on here, and also in that compressor, those pressure reliefs, they only protect the compressor. They do not protect your system. Meaning that if you isolate the compressor, closing the service valves, suction, and discharge, and you trap some CO2 in the compressor, that pressure reliefs will open and release the CO2 from the compressor only. If you isolate other parts of the system, that valve is not protecting anything else besides the compressor. So that is important to know, because some people, they believe because they have that pressure reliefs, that will protect more parts of the system. No, it doesn't. It's only for the compressor. We talk about leak detection and talk about also that CO2 is heavier than air. So what happens is, if we have a leak of CO2, the CO2, because it's heavier than the air, will come to the bottom on the floor and will displace the air to the top. So the best way to install leak detectors in this case will be close to the ground. We recommend to install those between 18 to 36 inches from the ground. At that point or that height, you will be able to read to detect the CO2 leak early enough that you can activate your systems. Can be ventilation systems, can shut down the system. Whatever systems you have to prevent the leaks, you can activate those. So 18 to 36 inches. Some people in the past, they were installing the leak detectors about 5 feet. 5 feet is kind of difficult, especially if my height is not too much. So 18 to 36 is much better.
What about lower? If it's lower than that, can you get a lot of false alarms?
Exactly, yes. It's lower, you get a lot of false alarms. This table over here shows what happens if we have leaks or high concentration of CO2 in some locations. It's important to know that CO2 is part of the air that we breathe all the time, right? So the regular concentration in the atmosphere is 400 ppms. If you have your leak detector and reading 400, 500, that will be normal. But if you read 5,000 or more, definitely it's not. Actually, more than 1,000 or 2,000 is something happening. There is a small leak somewhere. So check that. But if you're reading between 400 to 600, probably it's okay. That is the safety part. Now, the design overview. This is the part where we're going to talk about how the system operates, what the different concepts are, and why we need to have different technologies to make CO2 better. The use of CO2 systems basically has been done in order to reduce the use of HFC refrigerants, right? So we want to remove the HFC refrigerants for the applications. So there are different ways that we have been doing this and trying to get to the point that we have completely HFC-free systems. So the first line represents what we have now, a conventional system with only HFCs. You have HFC for your medium temperature cases and also for your low temperature cases. So it's 100% HFC charge. The first design that was done with CO2, it was to remove the low temperature loads from the HFC system. So in that case, we had HFC on the medium temperature application, but we changed the low temperature to have CO2 direct expansion. Still, we need HFC refrigerants for the medium temperature, and also this same HFC refrigerant is condensing the CO2 for the CO2 to operate in the low temperature loads. So by doing that, we were able to reduce the charge from 100 to 70%, 100% to 70%. Basically, we reduced 30% of the HFC charge in that case. Normally in supermarkets, you have seen that, we have more medium temperature load than the low temperature load. That is, every supermarket is that way, basically. That is why we only reduce 30%. So we still have a lot of HFC charge in the supermarket, right? So the next step is how can we eliminate the HFC from the medium temperature applications? Well, there are different ways that we can do that. We can use glycol, or we can use what we call a CO2 liquid overfeed. If we use glycol and CO2 DX on the low temperature, or we use glycol and CO2 liquid overfeed on the low temperature here, or if we use CO2 liquid overfeed medium temperature and CO2 DX medium temperature, the effect is basically the same. What we are doing here is just using different concepts on how we do this part. However, we always need the HFC either to chill the glycol and condense the CO2. So those three configurations, even we did different ways, in the end, the result is the same. We can go down only to about 15 or 30% of the total charge because we need this HFC refrigerant to chill the glycol or condense the CO2. It's just different configurations. Now, just quick explanation here. What is the difference between liquid overfeed CO2 and CO2DX? CO2DX is similar to what we have with HFCs. We use compressor, expansion valves, and evaporators. Nothing changed. CO2 liquid overfeed, that is a little bit different. In that case, we have a receiver, and we have CO2 pumps that will be pumping CO2 liquid to the display cases, operating similar to a glycol system with water pumps, but in this case will be CO2 pumps pushing the liquid into the display cases. That will be the difference. However, in the end, the effect is the same as we discussed that part.
So it's liquid going in, liquid coming out?
Yes. Well, 100% liquid going in, about 50-50 coming out, because the CO2, part of the CO2 evaporates in the display cases. With the glycol, you have 100% liquid coming in and liquid going out. CO2, you have a mix coming back. Yep.
Is there an advantage to using the flooded coil or liquid overfeed versus DX?
Yes, CO2 is more efficient. You have more surface area with the refrigerant. Your heat transfer is better. Yeah. Okay, so we have those. The next.
For that liquid overfeed, all they're doing is when they're coming back 50-50, that CO2 pump is just going back to the heat exchanger?
Actually goes back to the receiver.
Yeah, so it just comes back straight to the flash tank?
Yes. And from the flash tank with the heat exchanger, you take the vapor only and condense that back to the system. Yeah. The next iteration will be this one. When you have your CO2 in the store, But now we use a different refrigerant to condense the CO2. If we use, for instance, in this case, ammonia or propane to condense the CO2, then at that point we get to cascade system, which is completely HFC free. That is one option. But it's a little bit complicated, but that is options we have. However, we have this CO2 transcritical system. The CO2 transcritical systems is very similar to the HFC systems that we have. I can tell you that. If you are good with HFC systems right now, 80% of what you know and what you apply to HFC systems, you can apply directly to CO2 transcritical systems. They have the same principle of operations, the same components, is very similar. There are small parts, yes, that we need to be aware of, and we need to understand how they do operate, but they are very similar. With this, either the ammonia or propane with CO2 cascade systems or CO2 transcritical systems, we can meet the requirement of being HFC-free system completely, which is the goal in the end, right? So if we go through this a little bit again, but now in a graphic way, this will be what we know right now, HFC systems. You have your condenser, you have your HFC system, and you have your medium temperature and low temperature loads. That is what we know. If we change the low temperature and we add the CO2 system, now you will have this kind of configuration. Your condenser, your HFC system, this HFC is feeding your medium temperature, but also is feeding this CO2 portion to condense the CO2. And the CO2 is feeding your low temperature. So what you have here now is a cascade system in some portion, but the difference of the complication of this is that now you need to be good servicing an HFC system and also servicing a part of the CO2 system.
So those ain't compressors, they're just recirculator pumps.
No, these are compressors. This is the X portion. Yeah, direct expansion. Those are compressors. Mm-hmm. And for the end user, they need to have two pieces of equipment now instead of having only one. And they need more spare parts. They need to have two different refrigerants. So that gets costly and also complicated. If we change the medium temperature portion, instead of being HFC, we have glycol, the system becomes like this. You have glycol chillers here with pumps feeding your medium temperature cases. The CO2 doesn't change from the previous one. We still have the same. And you have your HFC. In this case, the HFC only chills the glycol here and only condenses the CO2 here. So again, the charge is reduced, but you still have HFCs in your system. And now you have HFC, glycol, and CO2 in the store. And the technicians, you guys need to be proficient managing all of this, right? So the system gets complicated even though we reduce the refrigerant charge. So that is what we were seeing in many cases. This is a new version of the CO2 system when we kind of reduce that complication a little bit. So this system here, we call that CO2 hybrid because in here we have compressors on this side and we have the liquid CO2 pump on this side. So this system can provide liquid overfeed for medium temperature and can provide CO2 direct expansion for the low temperature application.
So it's still considered the hybrid is still considered a cascade?
It's still considered a cascade, yes. Because this HFC is condensing the CO2 here, yes.
So you have pumps there though?
Even, yeah, but the pumps take the liquid from the tank once after it's condensed. So this is still a cascade system, yes. Actually, if you have more than one refrigerant, you will have a cascade system.
Okay, so it don't matter if it's a compressor
No matter
or a
what.
pump, it's a cascade. Okay.
Yes.
Got it.
Like at the glycol system, we consider secondary systems. In the end, it's a cascade system because you have the HFC chilling the glycol chilling the display cases. It's a cascade system. Yeah. So you have this option that we did in some stores. But if we go now to CO2 transcritical systems, the CO2 transcritical systems look like this, very similar to what we have with HFCs. You have your condenser or gas cooler, your CO2 system here, and your medium and low temperature loads that operate also with direct expansion. That basically we're coming back to what we had at the beginning with HFCs. The same concept, right? So what are some of the differences or benefits with CO2? With this, it's very similar to HFCs. You have only one refrigerant. You don't have multiples, only one. You have CO2, which is natural, is low cost, and also will be HFC-free. One of the things that we need to check or be aware here is the operating pressures. We mentioned CO2 is a high-pressure refrigerant. So now your pressures on the low temperature side will be between 180 to 200 pounds. On your medium temperature will be around 420 psis. We need to consider that now the flash tank, which in HFCs is equivalent to the receiver, will be at different pressure compared to the gas cooler or compared to the suction side, which will be about 500 psi, 420. And your gas cooler or condenser will be operating between 700 psi up to 1500 psi. So those are one of the things that you need to be aware of. Now, the CO2 systems can have about the same applications that we have with HFC. They can be a split suction temperature, when you have your medium temperature and low temperature, can be medium temperature only, or can be low temperature only as well. I do not recommend much the low temperature only, and I haven't seen many applications like that in the US. I have seen some in Europe, but not here. The problem with the low temperature only is that normally you will also require medium temperature compressors as well. So it's better to have them both combined, medium and low temperature. Looking at the system here, if we transfer that compressor rack into a kind of simplified piping schematic, you will see something like this. You will need low temperature compressors, medium temperature compressor, the gas cooler or condenser. I'm going to explain you why it's called gas cooler and condenser. Also now we need this high pressure valve. We have the flash gas tank. We have another valve here that we call flash gas bypass. And then you have your medium temperature and low temperature cases. Those cases, they will have similar components that you have with HFC. Either they have the case controllers with the electronic expansion valve. All of that doesn't change. It will change only the refrigerant that we are running to. So in HFC systems, you have your medium temperature and low temperature compressors discharging into one header, common header. Here, we can see that the low temperature compressors discharge into the suction of the medium temperature compressors. That is normally different from HFCs if you don't have like a compound cooling, compound compressor, things like that. So in normal HFCs, you don't have that configuration. So because of this, when people is doing startups in the system or a startup in the store, we need to have always running the medium temperature compressors first and then the low temperature compressors. That is very important when you are doing a startup. Having your medium temperature compressor running first, and then you can start your low temperature compressors. In HFC systems, which will be something like this, you don't have that problem, or do you have that concern? Because either you run the medium temp first or the low temperature, they discharge into the same header, and then you can have your system running. That doesn't change. So this will be something to notice if you're doing a CO2 systems startup. So this table here represents the main differences between HFCs and CO2 systems. We talked about some of those already, the discharge of the system, the low temperature compressors, the flash tank, the functionality of those between the receiver and the flash tank. In the HFC system, the receiver is basically like a storage tank. You have your receiver with your liquid there. In CO2, you have that as a flash tank. The function that it has is separate vapor and liquid, besides being kind of a storage receiver as well, or a storage tank. But in this case, the design of this tank is very important. If you have a vertical or horizontal receiver, that makes a little bit of the difference. In the end, the operation is the same, but it's a lot easier to separate vapor and liquid if you have a vertical receiver compared to horizontal receivers. So that is one of the differences here. The pressure inside the receiver, for HFC systems, your pressure is very similar to your condenser pressure, right? On CO2, that will be different. Normally, you will have few hundred pounds difference between your gas cooler and your flash tank pressure. That is something important to notice. And with that, now we see probably the next line, which says how many pressure levels you have in your system. In HFCs, you have only 3 normally: low temperature suction, medium temperature suction, and condenser. That's all. Well, with CO2, in addition to those 3, we need to add the flash tank pressure. You will have 4 now. 4 different pressure levels that you will need to be checking. The high pressure valve and the flash gas bypass valve, those valves, we don't use them on HFC systems. We have what we call the holdback valve and things like that. They do work, or they do some function similar, but it's not exactly the function that we need on CO2. On CO2, the high pressure valve basically controls the pressure in the gas cooler, and the flash gas bypass valve controls the pressure inside the flash tank. We'll explain that later. Materials, for HFCs, you use K and K-type copper. That's common. On CO2, we use those. In addition to that, we use a high-pressure copper, which is called K65 or XHP, or some people is using a steel piping as well. I'm not sure if you have heard the K65 copper, but basically it's an alloy between copper and iron. It has about 2% iron content that makes the copper stronger, and that can be used for high pressures. So that is why we need that K65 on the high side pressure of the system. Or, again, people use a steel pipe in that area as well. We talk about the operating pressures. This is an important one, the power outage. What happens in a HFC system if we lose power? If we lose power in the store and you don't have power for 1 hour, 2 hours, even 1 day or 2 days, in your HFC system, nothing happened, right? You don't need to consider basically anything. Well, with CO2, it's not the case. CO2, as we said, it has a very high coefficient of expansion, or expands really quickly. If we increase the temperature of CO2, it will increase the pressure. Well, if we have no power in the system, the CO2 is going to be idle and will be gaining heat from the ambient. By gaining heat from the ambient, the pressure will increase, increase, and increase. And what happens with that is that all the pressure reliefs that I told you that we have in the tank, in the suction side, in the gas cooler side, well, we can get to a point that we can actually reach the set point of those pressure reliefs and start venting CO2. That is one of the main complaints that we have heard about CO2. If they lose power, they start losing the refrigerant. If the end user loses, or the store loses the refrigerant, you lose your capacity of cooling your product, right? So that is the main issue that we have with CO2 right now. There are some solutions for that, and I will talk about those here. But the point here is HFCs, we consider those as a passive system because nothing happens if you lose power. With CO2, we call it an active system because you need to do something to prevent losing the charge just by gaining heat from the ambient. This is a chart. We're going through that. Basically, it's what happens inside the system when you are running with CO2. So in this case, let's start about the cycle from the medium temperature compressors. Your medium temperature compressors take the refrigerant, compress that from the suction temperature of these compressors all the way to the gas cooler inlet, right? So here at the inlet of the gas cooler, we have a high pressure and temperature CO2 going into the gas cooler. Now, I mentioned before, it's a gas cooler and condenser. Well, if your ambient temperature is about above 87 degrees, 85 degrees, most likely you will be in transcritical mode and you will not be condensing CO2. Above the 87 degrees and 1,000 pounds, the CO2 will not condense. That means it will not change phase from vapor to liquid. will be only vapor. So if that is the case, that we have only vapor, we are not condensing, so the unit is not called condenser. We are only cooling the gas from high temperature to a lower temperature, but it's still vapor or gas at the outlet. That's why it's called gas cooler. And that will be cooling the gas only when you are in high ambient temperature conditions, when you are above the critical point.
So 100% vapor?
Basically, yes. Some people call that a transcritical fluid, supercritical fluid. It's not actually.
I heard it was like 50-50, and then the vessel would complete the subcooling of that liquid, no?
No.
So it's 100% vapor.
It's actually
basically-
an undefined it's an undefined state at that time.
That's what they call undefined, but in reality, well, I can show you a schematic, will be basically vapor in the end. Yeah. So at that point, we have high pressure and temperature vapor going into the gas cooler. The gas cooler operates very similar to the condenser. It has fans, it has coil. Basically, we'll be rejecting the heat from that vapor to the ambient. So this operation is similar to the condenser, doesn't change. And from here, we have a cooler vapor coming out of that gas cooler and going into the high pressure valve. But it's only vapor, right? So when we enter the high pressure valve, which is in reality an expansion valve, it reduces the pressure from that fluid. When it reduces the pressure, at the same time reduces the temperature. So what happens is, at the outlet of that high pressure valve, we will have a mixture between vapor and liquid, okay? That is basically when you will see the change of state from that vapor going partially liquid and partially remains vapor. You don't have a full condensation in that case. Now, something important here is the higher the temperature that we have entered into the high pressure valve, the more vapor we will have inside the tank. If we have high temperature here at the inlet, we will have more vapor than liquid inside this tank. The cooler the temperature at the inlet of the valve, the less vapor and more liquid we will have inside the tank. And because we are doing refrigeration, we want to have as much liquid as possible inside this tank so that we can use that to cool the cases, right? So once we go through the process here, from the high pressure valve discharging into the flash tank, what happens there? We have vapor and liquid. Can we use vapor for refrigeration? No, right? So that vapor doesn't do anything for us. It's basically waste that we need to manage inside the system. So the way we do that, we take the vapor and pass that through this flash gas bypass valve and send that into the suction of the medium temperature compressors. Now, why do we need this flash gas bypass valve? Because we say the pressure inside the tank is higher than the pressure inside the medium temperature compressors. So we need to reduce the pressure here going into the compressors. Otherwise, we will be just backflow there. So we take this valve and take the flow of the vapor from the tank and send that into the suction of the medium temperature compressors. Now, what is the problem? The problem is that we are sending vapor into the compressors without doing any work. So what happens here is that these compressors, they will take this flow and send it back to the gas cooler, from the gas cooler to the valve, the tank, valve again, and just recirculate in this part of the system. That vapor will be just recirculating all the time. And what do we gain? We don't gain anything. We are just wasting energy to recirculate that vapor. That is why CO2 systems are inefficient or less efficient when we are in high ambient temperatures. Because remember, the higher the temperature at the inlet here, the more vapor we have. If we have a system that operates in Canada, when during winter time it's very cold, the amount of vapor that we are going to have here is minimum. So even we recirculate that amount of vapor, we don't waste almost any energy. That is why CO2 systems, they are less efficient when they are in high ambient temperatures. And that is why there are different technologies that we are using now to improve the efficiency of those CO2 systems when they operate in high ambient conditions. The rest of the system is similar to HFCs. You take the liquid from the flash tank and send that liquid into the medium temperature cases, and that goes back to the medium temperature compressor. And similar thing with the low temperature. We send the liquid to the low temperature cases and goes into the suction of the low temperature compressors.
Real quick on the flash gas bypass valve, we're reducing the pressure on the flash tank. We're getting rid now. Technically, if that flash tank is at 520, we're running a temperature of about 35 degrees.
Yeah.
Isn't that also helping to desuperheat the discharge gas of the low temp compressors?
Yeah, it does.
Okay, so
Yes, it does.
You will say at least you're gaining from that if in this setup we don't have a liquid dump to offset the superheat.
Actually, in the current units, in the actual units, you will have different ways to maintain the superheat on the compressors. I'll show you that, but we have a hot gas injection and liquid injection in case of high or low superheat.
But the flash gas bypass valve, as it's bypassing with that vapor being around 35 degrees or so, it is assisting with desuperheating the discharge gas in some sort of...
It does, because actually, that's the next part. Once we are here, and the flow goes into, go the other way, goes into the suction of the medium temperature compressors, here is a mix of those three different flows. Depending how much flow you have from the low temperature, how much you have from the medium temperature, and how much you have from this bypass, all of that mixes together and goes into the suction of the compressor. If in the end, your temperature is lower than you need for superheat, again, we have a hot gas injection that will increase that superheat. If that's too hot, then we have liquid injection that cools down. But yes, that is a mix of all these three flows going into the suction of the compressor.
Do you find that liquid or hot gas injection a better method than a heat exchanger?
You can control more. Yeah, you have better control. Yes. So this is, yeah.
Do you guys have anything on hot gas defrost? I was told that you guys were going to...
Hot gas defrost?
Defrost on CO2.
Yes, we don't have it here. We have a design for hot gas defrost. Yes, we do have that. Operates basically the same way. The difference, well, there are two different ways. I'm going to go real quick. There are two different ways. You can take the hot gas from the discharge of the low temperature compressors and take that for hot gas defrost, or you can take hot gas from the medium temperature discharge and use that for hot gas defrost as well.
You guys using live flow dryers, or how are you?
Well, from here, you need to have a valve that will increase your discharge pressure on the medium temperature compressors, because depending how you do it, you can have different flash. You can have a tank for hot gas defrost only, or you can take your flow going back to the flash tank. If you go back to the flash tank, you need to increase your discharge pressure on the low temps higher than the flow, hot back valve, to increase your pressure higher going to the flash tank.
What are they generally running on hot gas defrost, or you guys are running on hot gas defrost pressure?
Pressure will be above the flash tank, about 580.
Okay.
Yep.
So not too high.
No, not too bad. Well, for hot gas defrost, actually the pressure is not the important part. The important part is how hot is your gas going in, yes. And how much gas you have.
Still like a 20-minute hot gas defrost?
Yeah, it will be similar. Yeah.
Wouldn't you put a lot of stress on those coils?
Yes, that's why we do not recommend hot gas defrost, but there are some customers that they want to have hot gas defrost because they have been using hot gas all the time. With CO2, it's actually more stress than HFCs, yes. Yeah, but this is a customer specific, customer design, not design, customer wants. Yes. Yeah. Yeah, until now, all our systems, they are only electric defrost. We are doing the hot gas because it's a requirement. Yeah. So we talk about CO2 systems being inefficient on high ambient conditions, but in the end, what we want to do is to have CO2 systems that they can replace HFCs. In order to replace HFCs, they need to be HFC-free, and also they need to be as efficient or better than HFCs, right? Because if you're gonna pay more for one of these and you are gonna pay more in energy as well, it's like, no, shouldn't do that. Well, there are different technologies available now that can improve the efficiency of CO2 systems. I am listing those here, and notice that these operate on the high pressure side of the system. And there are a couple more that operate on the low pressure side of the system. Well, these technologies that operate on the high pressure side, those are technologies that will give you benefits when you are running in high ambient conditions. If you are running in low ambient conditions, those technologies will not provide you any benefit at all, okay? So we have adiabatic cooling. Adiabatic cooling is the most common used technology in the US, not in Europe, but in the US, yes. Probably at least 80% of the systems installations that they are in the US, yeah, I would say probably 80, maybe a little bit less, but not too much, they have adiabatic gas coolers. Everything else will have either parallel compression or air cool or another kind of technology, but the most commonly used is adiabatic gas cooling. Mechanical cooling, that is not very commonly used. You will see more of that probably in the next few years, but as of now, it was not very common, and that will tell you why. Parallel compression is not very commonly used either. This technology is being used again, but it's not common yet. We have ejectors and parallel compression. For the US, there are 1 or 2 installations, like at test installations, no more. Europe, they have many more than we have here. This ET technology, that is a patent technology for us. We are pushing that technology that helps reducing the use of water in the stores. So we have 1 installation, 3 coming, but this kind of new technology for the US.
It's reducing the water?
Eliminating the water use, eliminating basically the adiabatic gas coolers. And then we have the FTE technology. This is another technology from us, from Kysor.
Talk about it.
Excuse me?
Can you talk about how you guys are eliminating the water?
Yes, I will explain that. Yeah. This is the FTE technology, full transcritical efficiency. This is another patent. And then we have the liquid ejectors. That is a technology that operates very similar to ours, FTE, but we don't have that in the US applied yet. So let's go through those a little bit. This first schematic represents a standard booster system. Nothing changes. We know this concept is inefficient in high ambient conditions. That's what we know. That is the easiest way to do it, so let's do that. The next technology, or the first technology, will be the adiabatic gas cooling. Why is that the most commonly used? Well, it has a lot of benefits. It reduces the pressure that you operate in your system. Normally, if you are about 1450, with a adiabatic gas cooler, you can get down probably between 11 to 1200. Also, because you put water in the system, your cooling capacity increases a lot more. So your gas cooler reduces on size, but you have the water use in the store. Okay? So it provides energy benefits, provides space benefits, but at the end, the cost analysis, if you include the cost of the equipment, the water users, the maintenance that you need to provide, that's something that needs to be analyzed and decide, okay, I want to use this technology or there is something different. But again, this is the most commonly used. I'm not gonna tell which one is better. I will just provide the concepts and somebody decide what they want, right? So this is adiabatic gas cooling. The easy way to do it here, I missed that part, is you have an air-cooled gas cooler. You basically remove the connections going in and out from the gas, and then you put the adiabatic gas cooler, and you are done. It's really easy to make the change on this case. That is another reason why it's very commonly used. The next technology will be the external cooling or mechanical cooling. In this case, you have your regular system, and now we can add a plate heat exchanger at the outlet of the gas cooler with a small condensing unit connected to it. What it does is that if you have your gas cooler outlet temperature here, and then you have this cooling circuit, your inlet temperature at the high pressure valve is going to be lower than that. And we say the cooler the temperature at the inlet of the valve, the less vapor you have in your system, the less energy you consume to recirculate that vapor.
So what's going through the other side of the mechanical cooling?
Well, yes, this other side will have another refrigerant here. This will be like a cascade system here.
Okay.
So is that going to be like a refrigerant? So that's pretty much like a refrigeration unit just going through the piping frame.
Yes.
What refrigerant is in that?
Excuse me?
That's gonna have refrigerant though, right?
Yes.
That smaller unit.
Yes, and that's why it hasn't been used a lot, because the end users, they say, okay, I have a full CO2 transcritical system, HFC freeze, and you want me to put an HFC condensing unit? I said, no, I'm not doing that. But now that we have a small CO2 condensing units and propane units, they can use this concept easier than it was before, and still have a full natural solution. So that is why you will see this probably applied more than it was before.
Could that be used also similar, like, where they call it the charge saver design, where it comes off the receiver? Like,
Oh, the auxiliary
that would
condensing
cool down
units.
your temperature,
Yes.
but you wouldn't necessarily get it back to your flash gas tank.
Yes, that will be different purpose.
Yeah.
Yeah, that will be different purpose. I'll show you also, I have a slide for that. But will be the same concept. Instead of connecting this here, will be connected to the flash tank. Yeah, but this is the same concept, yeah. So we have this mechanical subcooling. Again, part of the reasons for not to use it was because HFC refrigerants, you require more maintenance. Not too big deal. So the next one will be a parallel compression. We talk about the issues that we have with the vapor inside the tank and the different pressures that we have between the flash tank and the suction of the medium temperature compressors, and that we use flash gas bypass valve over here. Well, this concept, what it does, it has another compressor that is connected directly to the flash tank. What is the benefit of doing this? Well, we know that the pressure in the flash tank is higher than the pressure in the medium temperature suction. So this compressor will be running at suction pressure same as the flash tank, which is already higher than the medium temperature suction, about 100 pounds at least. So this compressor will have better efficiency than those medium temperature compressors. It will be removing the same amount of flow that you have in your system, but running at more efficient conditions. And because of that, it will provide some energy benefits for the system as a whole.
So just because of a lower compression ratio then, that's it?
Yes.
But it's still doing what this is doing, but just at a higher suction?
Exactly.
Okay.
Yes, and that is one of the things that I want to mention, because this guy doesn't change how much vapor you have, doesn't change anything besides just recirculating in the better conditions, right? So this is the parallel compression portion. And the next one is what we call extreme temperature efficiency, or ETE system. This is the one that we have a patent for. And the way this system works is like this. We have, similar to the mechanical cooling, we have a plate heat exchanger connected to the outlet of the main gas cooler here. The difference here is that we take some of the CO2 coming from the gas cooler and we send that through this expansion valve and then go into the plate heat exchanger. And from that, we'll go to the suction of this AT compressor. So basically, this is a mechanical cooling circuit inside the same compressor rack. What is the effect of this? The effect is that we have a much lower temperature here at the inlet of the high pressure valve compared to at the outlet of the main gas cooler. So we produce less vapor inside the flash tank, and that produces less energy waste with the medium temperature compressors. Now, another part or another benefit here is that this ETE compressor is like a third suction group, operates separate from the flash tank, from the medium temperature compressors, and from the low temperature compressors. So in the parallel compressor, we saw that it was taking the vapor from the flash tank. So it has a limit on the pressure, on the suction pressure that it can operate at. This circuit is independent. So we run this compressor normally about 650 PSIs, which is much higher than the flash tank. So this compressor is actually more efficient than the parallel compressor. In addition to that, we produce cooling in this plate heat exchanger, and we reduce the amount of vapor that we have in the flash tank. So you have multiple benefits in this system that you don't have with the parallel compression.
Why run it at 650?
Because it's more efficient.
The low end on the gas cooler 700?
Say that again?
The low end on the gas
Oh, yes, that will be the minimum condensing temperature on the gas cooler. But this 650 is the suction pressure of this. But remember, if that's the 700 condensing pressure here, that means you are in low ambient conditions.
And they're making up something like the headmaster for that too, right?
Yeah. Yeah. And again, this technology, as the other ones that I explained, they will operate in high ambient conditions only. So in high ambient conditions only, your pressure in the gas cooler should be above 1,000 pounds easily.
How about like split condensers, running like an oversized 50% or
A
20%?
split condenser is another option. Yeah, it's another option that has been explored, can be used. Also, those gas coolers, all of them have easy motors, so you have the variable capacity on the easy motors. So there are different options and technologies being used, yes. But the split condenser will be used more for low ambient conditions than high ambient conditions.
So that suction, Ignacio, is coming from the plated frame. It's dumping into the common suction of the medium temp compressor. That's not like a
This one?
standalone. Yeah.
No, this one is a satellite compressor.
Oh, it is a
It's a satellite compressor. Yes, it is.
But it
It
still
is.
dumps it to the same discharge, right?
Yeah, the discharge is the same,
Okay,
but the
just-
suction is different. Yeah, the suction is different. It's a satellite compressor.
You're at 650 suction.
Yeah. So this is a more efficient system than the parallel compression portion.
Do you design that, your load as if you didn't have that ETE compressor available, like medium temp compressors could take flash gas load?
Yes, a little bit. Yeah.
They try to balance
We do first the calculation, how much cooling we can get here, and based on that cooling, we select the other compressors at the same operating pressure with a different gas cooler outlet temperature. Yeah. Okay, any more questions? Well, those technologies operate on the high side. Now let's look at the technologies that operate on the low side. Well, one of those is the full transcritical efficiency. This technology operates on the low side, on the low pressure side of the system, and the piping changes like this. So we have now, and the principle of operation of this system is basically about the superheat of the medium temperature cases. In HFC systems and everything, you have superheat that you set the expansion valves for what reason? Why do we need superheat on the cases?
Protect the compressor.
Protect the compressor from liquid coming back to the compressor, right? So when we have superheat at the case, and we have heat gains in the system in the suction lines. So we have plenty of superheat there. But what happens is, if you have superheat at your display case, you are using part of the coil to create that superheat instead of using all the coil to produce cooling for the product. So there is a calculation that it says about 80% of the coil is used for cooling, and about 20% of that coil is being used for superheat. So basically, we are wasting 20% of our coil for superheat instead of producing cooling. So when we do the FTE, instead of having that 8 degrees or 8 degrees for superheat, we reduce the superheat on the medium temperature cases down to 1 or 3 degrees superheat. That means we will have more refrigerant, and we will have more surface area for cooling instead of superheating, right? So if we do that, basically, the medium temperature cases, they will have more capacity at the same conditions. We are just putting more refrigerant through that, so we have more cooling capacity in the same display case. If we have more cooling capacity with the same case, that case, basically, we are making more efficient the case, right? So we can increase the suction temperature of this case. Instead of, let's say, assuming that it was running at 20 degrees, we can increase probably 23, 24 degrees, because now we have more cooling capacity in the same display case.
So running the case at a higher temperature,
Basically, yes,
more efficient.
more efficient. And what happens there is the cases, they drive the suction temperature of the medium temperature compressors. So if we are increasing the temperature, the suction temperature of your case, you can also do the same with the compressors.
That's money to run.
Yes. So when we do that, for every degree that you increase your suction temperature in your compressors, you are increasing your efficiency of those compressors about 1.8 degrees, 1.8%. So if we can increase the suction temperature in about 4 or 5 degrees, you can increase your compressor efficiency about 9%. So that is one way that you can make your systems more efficient. So that is what we do here at the medium temperature. But probably you notice that we have this liquid line, this solenoid on the liquid line feeding the low temperature cases. Well, what happens here is once we drop the superheat, we don't be able to fully evaporate all the refrigerant that we are passing through those cases. So at the end, we will have liquid or a small amount of liquid coming out of the medium temperature cases, and that is why we do have this FTE tank. Basically, think like a big suction accumulator, right? So the liquid that we have here, we collect that into the FTE tank, and from the top, we take only vapor going into the suction of the medium temperature compressors. So we still protect the compressors. Because we send vapor only. We don't send liquid, but we do have vapor and liquid in this FTE tank. So when we have enough liquid on the FTE tank, we can send a signal to this solenoid valve to close. When this valve closes, we don't have more refrigerant coming into the low temperature cases. The compressors, they don't know that we close the valve, so they keep running, and at some point, the pressure in this line is gonna be less than the pressure in the FTE tank. And just by pressure differential, the liquid from the FTE tank is gonna flow and feed the low temperature cases and go back to the low temperature compressors. In that case, when we take the liquid from the FTE tank, we are taking the liquid and the oil at the same time because they are miscible. And we are picking up everything from the bottom of the tank. So we take the liquid and the oil, feeding the low temperature cases, and that feeds also the oil going back to the low temperature compressors. So we don't have oil logging problems in this system because we are taking that oil going to the low temperature compressors as well.
Sounds great in paper,
Yeah.
but these guys have to fix it.
Well, if you are going to atmosphere in June, there will be some people presenting a study on this. And there is an installation in Minneapolis, which is cold, and they have about 8% energy benefits. Yeah. And that is the other part about this system. This system, because all the operation here is below the flash tank or at the flash tank and below, that doesn't care about what happens on the gas cooler. Can be hot, can be cold. This technology operates on the low pressure side, so it's completely independent of the ambient conditions. That's why Minneapolis is a good place to do this study because it's cold. You don't get the benefits of the high ambient conditions. So, yeah. Okay. Part of making the systems more efficient is we have technologies that operate on the high side. We have technologies that operate on the low side. So what about if we combine them? If we combine them and they are independent technologies, we can get the full benefit of those technologies in the same system. So this is an example that we can combine the ET technology and the FT technology in the same system, and you get the full benefit. During high ambient conditions, you get the benefit of the FTE and the ETE and the FTE at the same time. When you are in low ambient conditions, you get the benefit of the FTE. So that is one way to combine technologies. Another way will be like this. You can have a adiabatic gas cooler and also FTE technology on them. And again, those are independent technologies. You get the full benefit of both of them. Another option will be like this. You have adiabatic gas cooler and parallel compression. In this case, they are not completely independent because the parallel compression depends of how much vapor you have in the flash tank, and the adiabatic gas cooler, part of the benefits that they have is that they produce less vapor in the flash tank. So these are not completely independent technologies, but still you can get some benefits if you have a parallel compression with an adiabatic gas cooler. So again, the whole point of this is making the CO2 systems more efficient. Subsystems and components. Every system has their own parts, and we need to be aware of what we need to control, how we need to manage those options. So this is the piping schematic of one of the units. And you can see it's kind of complicated, but the purpose is not go through this. It's just to show you the operating pressures of the system, what we have now. We mentioned about these numbers, the 200, 420, 420 here, 520 on the flash tank, and 17 to 1400 on the gas cooler. So that is what we have for almost any system. But if we want to manage one of those systems, we need to have controls or system management for these portions of the system. We need to manage the gas cooler. The gas cooler is different management compared to the condenser. The condenser is normally managed based on TD. The gas cooler is based on pressure and temperature. That's a little bit different. We need to manage the flash gas tank pressure, the oil system, and the superheat for the compressor so that we ensure that they have the proper superheat, and of course the refrigerant. So for the gas cooler, we discussed about adiabatic gas coolers, but we also have air-cooled gas coolers. Normally, air-cooled gas coolers, they will be installed in cooler climates. Adiabatic will be installed in hot climates with low humidity. That's the idea. But honestly, there are customers that they specify adiabatic gas coolers anywhere, including Alaska. Yes, including Alaska. Yes. So, but they, because it's simple, they think if they put one technology, everybody can manage it. But anyway, they specify adiabatic gas coolers everywhere.
And how do they not freeze the water in Alaska?
Well, they don't need water. They don't put water on it. They just don't put water. They want it dry. Yes.
Oh, but they still put out.
Yeah, they just want it dry because they don't need it.
Just in case.
Yeah. So, but part of the benefits of this is that all of them have easy motors, as we mentioned before. The adiabatic gas coolers, and there are different manufacturers. Some of them, they do recirculate the water that they use. Some others, they don't. So some will consume more and less water, depending what is the vendor. To manage the gas cooler, we have these different components. We have a temperature sensor at the outlet of the gas cooler. We have a pressure transducer very close to the inlet of the high pressure valve. And of course, we have the high pressure valve. And there are, of course, controllers that will be reading that information and telling the high pressure valve what to do. In a transcritical system, the gas cooler is operated based on pressure and temperature, mostly pressure. What happens is there are studies, depending on the gas cooler outlet temperature, there are some calculations that the control does and defines or determines what is the optimum pressure for the system to operate. That optimum pressure basically refers to what is the highest efficiency that they can get based on those conditions. Every controls manufacturer, they have their own equation or algorithm that they use the gas cooler outlet temperature and calculate what will be the optimum pressure for the system to operate. Once they calculate that pressure, they are already reading this pressure that is coming from the gas cooler. So they compare those two pressures. If they don't match, they will open or close the valve trying to match those pressures. Because according to the conditions they have, that is the highest efficiency point for the system at that moment. So in CO2 transcritical systems, you will see the gas cooler pressure going up and down, up and down, up and down, because that depends on the gas cooler outlet conditions. It's not stable, your pressure will not be stable as well. It is important to install this temperature sensor about 6 to 12 inches, maximum 18, from the gas cooler outlet. You want to have the more accurate information that you can get. So the closer that you install that in the gas cooler, the better it will be for your system to read and see what it's doing. So that is important for us to operate. These valves here are some examples of the valves that they are in the market. Danfoss has, Carel, Emerson, or Copeland now, Sportland. All of them have valves that you can apply for these kind of controls. The flash tank, The flash tank is controlled based on pressure only. We have a pressure transducer installed somewhere here at the inlet of, should be here, close to the flash tank. But again, the controller is taking that pressure reading, and it's based on set point only. If we say the pressure in the flash tank has to be 520 psi, the controller is reading that pressure. If it's not that 520, it will open or close the flash gas bypass valve to get to that set point as close as possible. That's what the controller is doing. That's what the flash gas tank is managed, just based only on pressure. The flash gas bypass valve is the one that actually manages the pressure on the flash tank. So here is the valve. The pressure transducer is here, and this is the high pressure valve. So based on this pressure reading, this valve will open or close. And those are the type of valves that we can use. They are very similar to the high pressure valves. In some cases, the difference is just the pressure rating that they are applied for. Like these Danfoss valves, for some they call CCMT as in Thomas in the end. For the flash gas bypass, they are only CCM. The T means transcritical, that means goes in the high side. The not T means subcritical, which is lower pressure rating only. Something that is important here, some of those valves, there is no way that you can manipulate those in the field in case they fail or they stuck open or closed. So there is no much access that you can have through the controller or if you lose power. However, they have this tool from Sportland that basically is a signal generator. You can connect the valve to these 4 points here, and you can force the valve open or close as needed. In case of failure, you can open or close the valve and then keep the system running. So this is a tool that you can find very useful in some cases. The oil system, there is oil system which is high pressure system or low pressure oil system. The difference between high pressure and low pressure will be what is your pressure in the oil reservoir. The low pressure oil system, they run about the same pressure as the flash tank because there is a line that connects the oil reservoir into the flash tank for equalization pressure. So in this case, your pressure in the receiver will be same pressure as you have in the flash tank, which we already know that is higher than your medium temperature suction pressure and your low temperature suction pressure. So that ensures that you will have a positive pressure always to push the oil into your compressors when needed. The high pressure oil system, in that case, the oil reservoir pressure will be same as the medium temperature compressor discharge pressure. You will have a high pressure oil system. Your pressure will be probably 1,200 pounds, 1,300 pounds, depending what is the discharge of the medium temperature compressor. Those components here will be the oil regulators that we have here on the compressors installed. They are rated for the proper pressures, either operating pressures or pressure differential that they can manage to inject the oil in the compressors.
With those flare connections hold that pressure?
Yes. Yes. Also, the hoses that we use, they are rated for 120 bars. So yes.
You guys don't see a lot of leaks there?
No,
Not yet.
not yet. You just jinxed it.
Not yet.
Someone walks over and steps on it.
Yeah. Well, we have been installing systems since 2015, and they are very reliable.
Ignacio, I have a question.
Yes.
You guys make cases as well. Are you guys seeing aluminum coils on CO2 cases?
No, we don't use aluminum for the coils. The serpentine is copper, the aluminum fins only, but no, I know there is a manufacturer with aluminum coils.
We're having a bunch of leaks. They're the
Bunch of
only
leaks.
ones that we're seeing aluminum
6
coils on.
coils returned under warranty already.
Oh, really? Oh. Yeah, no, we don't use aluminum for that. No.
Thank you.
Yeah.
Happy to hear it.
This is for the superheat portion on the compressor side. As we mentioned, depending on the flows that you have from the low temperature cases, medium temperature, or flash gas, you can get into a condition that you can have either low superheat or high superheat. So in this case, assuming that you have a low superheat, we have this solenoid valve that is connected to the compressor discharge over here, and connected in the suction line of the medium temperature compressors. If we detect low superheat, this valve will open and inject hot gas into the suction of the medium temperature to increase the superheat needed. If we have a high superheat, assuming we have too much flow from the low temperature compressors, we have this other valve over here, which is the same as there, which is a liquid injection valve. We take liquid from the main line from the flash tank. We have an expansion valve here and inject that liquid into the suction of the medium temperature compressors, reducing the superheat and maintain the superheat at the stable conditions as needed. This is the auxiliary condensing unit that you were talking about. When you lose power, again, the CO2 gains heat and start increasing the pressure and temperature. So one of the ways that we have to keep the CO2 for longer time inside the system is to install these auxiliary condensing units. We connect the plate heat exchanger on one side to the flash tank, on the other side the auxiliary condensing unit, and that will help us to maintain the CO2 at lower pressures because it will take the vapor from the top, condense that CO2 here, and send it back to the tank. So we'll be only recirculating the vapor produced in the tank, and that will help us to maintain for longer time the CO2 inside the system. Heat reclaim. Heat reclaim is a topic that a lot of people talk about, and they say, oh, you can get a lot of heat from CO2 systems. Yes, you can. When you are in high ambient conditions. The problem is that you need the heat when you are in low ambient conditions. So in low ambient conditions, because your system operates below the critical point, you have subcritical conditions, is very similar to what you get with HFCs. So you will be on this area, below this point, you will be on this area when you are in low ambient conditions. So the amount of heat that you can get is well reduced compared to this number you were around here in cold ambient situations. The benefit or the advantage of CO2 is because we have the high pressure valve. We can manipulate that valve to increase the discharge pressure. Well, if we close the valve, assuming we close the valve, that increases the pressure of the medium temperature compressors, and then we can move from this point all the way up to this point or this other point. We can do that artificially with the valve and the controls. However, that is not free. We will be penalizing the compressors because they will be running at higher pressure when they don't need. So that's a balance again. We want heat, yes, but how you want to pay for that? With the compressors or with another kind of heat? It's not free. But it's a possibility that you can use there. Controls portion, this is just in general what controls are available. Yeah. What is available? So you will need all of these systems here, site manager, compressor controls, high pressure valve, case controllers, electronic expansion valves. So those are the site managers from different manufacturers. Probably you have seen most of them. Copeland, Emerson, Danfoss, RDM, Microthermo, all of them can manage CO2 system now. Of course, if they can manage the store with CO2 system, they have components for compressors. The only point here is that some of them, they have standalone components specifically for compressors. Some of them have already everything integrated in one component. Like this Carel component or that RDM, they do manage the compressors and high pressure valve and flash gas bypass valve with the same module. They don't need separate modules. Some others, they need separate modules. This will be the modules for the high pressure valve and flash gas bypass valve. This is the Microthermo and Copeland solutions. Again, the Carel has their own. Danfoss, they had their own before, but they eliminate that and now use the stepper boards. So there's a different integration, but they can do it. That is not a question. Case controllers, there are multiple case controllers from different manufacturers. They basically operate the same. Some of them have different features, but basically they control all of that part of the case. Defrost, lights, anti-sweat, temperatures, everything. Expansion valves, electronic for CO2, no question about that. There are pulse modulating valves or stepper valves. The main difference between the two will be either the capacity. The pulse modulations, they are lower capacity than some of the steppers. Steppers, they can manage bigger loads. The other difference will be in case of power outage, the pulse modulation, they will fail closed. The steppers, they will remain at the position that they were at that moment. So if we lose power, in order to protect the compressors, we either close those valves in two ways, either with a capacitor or something, or we put a liquid line solenoid upstream the valve so that we prevent any liquid going to the compressors. And this is the last slide. Some of the safeties that we consider in the system are these. We talked about the first two already. The third one is reverse acting for the gas cooler. Normally, in this case, because we can get to the point when we have higher pressures in the system, we do the reverse acting on the gas cooler fans. If we have a 0 to 10 volts, we actually reverse that to 10 to 0, meaning that 10 volts is the fans will be off, 0 volts, the fans will be running 100%. Because it's common that you can lose the signal from your system. Even you don't lose the power, you can lose the signal. And if you get 0 volts in the gas cooler, they will be running 100%. What happens there, you have excess capacity, you have things like that. But that will not shut down your system. If you have the 0 to 10, and you get 0, your fans will be off, and then you have high pressures, and the system shuts down. So that's an important thing to know. Backup power for controls is important. Normally, if you lose power, it's very useful if you close your high pressure valve and your flash gas bypass valve, because in that case, you isolate the pressures in your system, and you can have more time with the system, with the CO2 inside the system. Refrigeration load management protocols, similar way. If you lose power, once the power comes back on, you don't want all the cases to start running at the same time. That causes problems on the suction line size with the pressures. You have a lot of vapor or CO2 going back to the compressors, and that creates a lot of pressure, overpressure on the suction lines of your system, and your pressure reliefs can start popping up. And high pressure switches for compressors, that's a regular safety feature on the compressors. If they get to high pressure, they should shut off. Thank you very much for your time.